Dark oxygen, a term that may sound paradoxical, refers to a newly discovered form of oxygen that plays a crucial role in our understanding of both Earth's early atmosphere and the potential for life beyond our planet. This intriguing discovery emerged from research that delved into the chemical processes that shaped our planet's environment billions of years ago. Scientists have long speculated about the composition of Earth's primordial atmosphere, and the identification of dark oxygen has provided significant insights into the conditions that may have fostered the emergence of life. This form of oxygen, which interacts differently with light and other elements, suggests that our planet's atmosphere was far more complex than previously thought. The implications of this discovery extend beyond Earth, as they open up new avenues for exploring the atmospheres of exoplanets. By understanding how dark oxygen functions, researchers can refine their models for detecting signs of life on distant worlds. This newfound knowledge could revolutionize our search for extraterrestrial life, as it highlights the possibility that life could exist in environments previously deemed inhospitable. The excitement surrounding dark oxygen lies not only in its scientific significance, but also in the mysteries it presents. As we continue to unravel the complexities of our own atmosphere, we are reminded of the vast unknowns that still exist in the universe. The prospect of finding alien life based on this understanding is both thrilling and daunting. It challenges our perceptions of what constitutes a habitable environment and encourages us to think creatively about the forms life might take in different atmospheric conditions. Engaging with this topic invites us to ponder the fundamental questions of existence. What does it mean to be alive? How do we define life in the context of the cosmos? The discovery of dark oxygen serves as a catalyst for these discussions, igniting curiosity and wonder about our place in the universe. As we venture further into the realms of space exploration and astrobiology, the implications of dark oxygen will undoubtedly shape our understanding of life, both on Earth and beyond. The excitement surrounding this topic is palpable, as it not only enhances our comprehension of our planet's history, but also propels us toward the possibility of discovering life in the far reaches of the cosmos. In this age of exploration, dark oxygen stands as a beacon of hope and intrigue, urging us to continue our quest for knowledge and understanding in the vast, mysterious universe. Recent explorations of the Pacific Ocean floor have unveiled astonishing findings regarding the presence of dark oxygen, a phenomenon that has captivated the scientific community. The conditions on the ocean floor, particularly in the Pacific, are characterized by extreme pressure, low temperatures, and a unique geological landscape that includes ancient metallic rocks. These rocks, primarily composed of iron and other metals, create an environment ripe for unexpected chemical reactions. Researchers discovered that these metallic formations can generate electricity through a process known as geoelectricity, which occurs when seawater interacts with the minerals in the rocks. This interaction not only produces electrical currents, but also facilitates the release of oxygen in a manner that was previously unanticipated. The implications of this discovery are profound, as it suggests that the ocean floor could be a significant source of oxygen, challenging our traditional understanding of how oxygen is produced in marine environments. The scientific community's reaction to these findings has been one of excitement and intrigue. Many researchers were initially skeptical about the idea that metallic rocks could play such a pivotal role in oxygen generation. However, as more data emerged from the sensors deployed on the ocean floor, it became increasingly clear that this unexpected source of oxygen could reshape our understanding of marine ecosystems and their dynamics. The discovery has prompted a flurry of research aimed at further investigating the mechanisms behind this process and its potential implications for oceanic life. Scientists are now exploring how this dark oxygen interacts with existing marine organisms and whether it could support life forms that thrive in extreme conditions. Moreover, the implications extend beyond Earth, as this discovery raises questions about similar processes that might occur on other celestial bodies. If ancient metallic rocks can generate oxygen in the depths of our oceans, could similar mechanisms exist on other planets or moons? This line of inquiry has sparked renewed interest in astrobiology and the search for extraterrestrial life, as researchers consider the potential for life in environments previously thought to be inhospitable. In summary, the initial findings of oxygen sensors on the Pacific Ocean floor have unveiled a groundbreaking source of dark oxygen generated by ancient metallic rocks through geoelectricity. The scientific community's enthusiastic response underscores the significance of this discovery, as it not only enhances our understanding of Earth's oceanic processes, but also opens new avenues for exploring the potential for life beyond our planet. The excitement surrounding these findings is palpable, as they challenge existing paradigms and inspire further investigation into the mysteries of our oceans and the universe. The Central Intelligence Agency, CIA, has a storied history of involvement in covert operations, and one of its most intriguing endeavors was Project Azorian, initiated in the 1970s. Officially, the project was presented to the public as a deep-sea mining operation aimed at extracting valuable minerals from the ocean floor. However, the true objective was far more clandestine: to recover a sunken Soviet submarine, the K-129, which had gone down in the Pacific Ocean. The CIA employed a specially designed ship, the Hughes Glomar Explorer, to carry out this mission under the guise of commercial interests. While the project was shrouded in secrecy, it ultimately revealed significant insights into the ocean's geological resources, particularly the discovery of polymetallic nodules. Polymetallic nodules are rock concretions found on the ocean floor, composed of various metals including nickel, copper, cobalt, and rare earth elements. These nodules form over millions of years through the precipitation of minerals from seawater, making them a valuable resource for modern technology. The properties of these nodules are particularly noteworthy. They are rich in essential metals that are crucial for manufacturing batteries, electronics, and renewable energy technologies. The discovery of these nodules during Project Azorian not only highlighted the potential wealth hidden beneath the ocean's surface, but also underscored the strategic importance of oceanic resources during the Cold War era. The historical significance of Project Azorian and the discovery of polymetallic nodules extends beyond their immediate economic implications. The project marked a pivotal moment in the intersection of intelligence, technology, and environmental science. As researchers today delve deeper into the ocean's depths, the findings from Project Azorian continue to inform current scientific research. Modern studies are increasingly focused on understanding the ecological impact of mining these nodules and the potential for sustainable practices in resource extraction. Furthermore, the implications of these historical findings resonate in contemporary discussions about resource management and environmental conservation. As the demand for rare metals surges in the context of green technologies and renewable energy, the lessons learned from Project Azorian serve as a cautionary tale about the balance between exploitation and preservation. Scientists are now exploring innovative methods to harness these resources while minimizing ecological disruption. reflecting a growing awareness of the need for sustainable practices in oceanic exploration. In summary, the CIA's Project Azorian, with its cover story of deep-sea mining, led to the discovery of polymetallic nodules, which hold significant historical and contemporary relevance. The project not only revealed valuable resources, but also laid the groundwork for ongoing scientific research that seeks to balance technological advancement with environmental stewardship. The legacy of Project Azorian continues to shape our understanding of the ocean's potential and the ethical considerations surrounding its exploitation. The discovery of dark oxygen and its potential role in the evolution of life on Earth opens up fascinating avenues for understanding how life may have adapted to its environment. One significant aspect of this discussion involves polymetallic nodules, which are not only valuable for their mineral content, but also play a crucial role in generating oxygen and supporting diverse ecosystems on the ocean floor. These nodules, rich in metals like nickel, copper, and cobalt, create unique microenvironments that can influence the surrounding biological communities. The chemical processes associated with these nodules, particularly the geoelectricity generated by ancient metallic rocks, may have contributed to the production of dark oxygen, providing a vital resource for early life forms. Research has shown that a variety of species thrive in the vicinity of polymetallic nodules, showcasing the intricate relationships between geological formations and biological diversity. These ecosystems are often characterized by unique organisms, including specialized bacteria, tube worms, and various invertebrates that have adapted to the specific conditions created by the nodules. The presence of dark oxygen in these environments could have facilitated the development of these species, allowing them to exploit the chemical energy available in their surroundings. This adaptation highlights the potential for life to thrive in extreme conditions, challenging traditional notions of what constitutes a habitable environment. Moreover, the implications of dark oxygen extend beyond the organisms currently known to inhabit these ecosystems. The possibility of alternative life forms that utilize electricity instead of sunlight for energy is a captivating concept that has gained traction in scientific discussions. Just as some bacteria can metabolize chemicals in hydrothermal vent ecosystems, it is conceivable that life forms could evolve to harness the electrical energy generated by the interactions between seawater and metallic rocks. This paradigm shift in understanding life's energy sources opens up exciting possibilities for the existence of organisms that thrive in environments devoid of sunlight, such as the deep ocean, or even extraterrestrial settings. The exploration of how dark oxygen could have influenced the evolution of life on Earth encourages a reevaluation of the conditions necessary for life to flourish. It suggests that life may not be limited to the familiar processes of photosynthesis and respiration, but could also encompass a broader range of metabolic pathways. As scientists continue to study the interactions between polymetallic nodules, dark oxygen, and the ecosystems they support, we may uncover new insights into the resilience and adaptability of life. This exploration not only enriches our understanding of Earth's biological history, but also informs the search for life beyond our planet, as we consider the myriad ways life could potentially arise in diverse environments throughout the universe. The discovery of dark oxygen has profound implications for the search for extraterrestrial life, particularly in the context of NASA's missions to celestial bodies such as Europa and Enceladus. These icy moons of Jupiter and Saturn, respectively, have long been considered prime candidates for harboring life due to their subsurface oceans, which are believed to be in contact with rocky sea floors. The presence of dark oxygen generated through unique geological processes, suggests that similar mechanisms could exist on these moons, potentially creating environments conducive to life. As NASA continues to explore these moons with missions like the Europa Clipper and the upcoming Enceladus Orbilander, the concept of dark oxygen encourages scientists to broaden their search criteria for biosignatures and life-supporting conditions. The implications of dark oxygen extend beyond Earth, as it raises the possibility that this form of oxygen could exist on other celestial bodies. For instance, if ancient metallic rocks can generate dark oxygen in the depths of our oceans, similar geological formations on Europa or Enceladus could produce it as well. The interaction between the ocean water and the rocky mantle beneath these moons may lead to the generation of electrical currents and the subsequent release of dark oxygen, creating a unique chemical environment that could support microbial life. This understanding shifts the focus from solely searching for oxygen, produced by photosynthesis, to considering alternative pathways for oxygen generation, expanding the scope of astrobiological research. Moreover, the discovery of dark oxygen highlights the potential for life in environments previously deemed inhospitable. Traditionally, the search for extraterrestrial life has concentrated on planets and moons with conditions similar to Earth, particularly those with liquid water and sunlight. However, the existence of dark oxygen suggests that life could thrive in extreme environments, such as the dark, cold oceans beneath the icy crusts of Europa and Enceladus. These environments may host organisms that utilize chemical energy or electricity rather than sunlight, challenging our understanding of life's adaptability and resilience. As scientists continue to investigate the implications of dark oxygen, they are prompted to rethink the criteria for habitability. The potential for life forms that rely on alternative energy sources opens up new avenues for exploration, encouraging missions to investigate not only the surface conditions of celestial bodies, but also their subsurface environments. This shift in perspective could lead to groundbreaking discoveries, as researchers seek to understand how life might exist in the most unexpected places. In summary, the discovery of dark oxygen significantly expands the search for extraterrestrial life by informing NASA's missions to moons like Europa and Enceladus, suggesting that similar processes could occur on these bodies. It also emphasizes the potential for life in environments previously thought inhospitable, encouraging a broader understanding of the conditions under which life can thrive. As we continue to explore the cosmos, the implications of dark oxygen will undoubtedly shape our quest to uncover the mysteries of life beyond Earth. The ecological impact of deep-sea mining, particularly the harvesting of polymetallic nodules, raises significant concerns regarding the health of ocean floor ecosystems. These nodules, which form over millions of years, are not just valuable sources of metals like nickel, copper, and cobalt. They also play a crucial role in supporting diverse marine life. The process of mining these nodules can lead to severe disturbances in the delicate balance of deep-sea ecosystems. When the ocean floor is disturbed, it can result in the destruction of habitats that are home to unique organisms, many of which are still not fully understood by scientists. The removal of these nodules can disrupt the intricate relationships between species, leading to a decline in biodiversity and potentially causing irreversible damage to these ancient formations. The consequences of harvesting polymetallic nodules extend beyond immediate ecological disruption. The sediment plumes generated during mining operations can smother nearby marine life, blocking sunlight and affecting photosynthetic organisms. Additionally, the release of toxic substances trapped within the nodules can further threaten the health of marine ecosystems. As these ecosystems are interconnected, the impact of mining can ripple through the food chain, affecting not only the organisms living in the vicinity of the mining sites, but also those that rely on them for sustenance. This interconnectedness underscores the importance of considering the long-term ecological consequences of deep-sea mining. Preserving these ancient formations is vital for future research and understanding of marine ecosystems. Polymetallic nodules are not only valuable for their mineral content, but also serve as a record of geological and biological history. Studying these formations can provide insights into past climate changes, oceanic conditions, and the evolution of marine life. By protecting these resources, we ensure that future generations of scientists can continue to explore and learn from the ocean's depths, potentially uncovering new knowledge that could benefit humanity. The challenge lies in finding a balance between resource extraction and environmental sustainability. As the demand for rare metals increases, particularly in the context of renewable energy technologies, the pressure to exploit ocean resources intensifies. However, it is crucial to approach deep-sea mining with caution, implementing stringent regulations and sustainable practices to minimize ecological damage. This includes conducting thorough environmental impact assessments, establishing protected areas, and investing in research to develop less invasive extraction methods. To sum it all up, the ecological impact of deep-sea mining on the ocean floor and its ecosystems is a pressing concern that requires careful consideration. The potential consequences of harvesting polymetallic nodules can lead to significant disruptions in marine life and biodiversity. Preserving these ancient formations is essential for future research and understanding of our oceans. Striking a balance between resource extraction and environmental sustainability is imperative to ensure that we do not compromise the health of our oceans while meeting the growing demand for valuable resources. As we navigate this complex issue, it is essential to prioritize the long-term health of marine ecosystems alongside economic interests. The ongoing discussions among scientists regarding dark oxygen and its role in Earth's history reflect a vibrant and sometimes contentious field of research. As researchers delve into the implications of this newly discovered form of oxygen, differing opinions have emerged about its significance in shaping the early atmosphere of our planet. Some scientists argue that dark oxygen could have played a pivotal role in the development of life by providing a unique chemical environment that facilitated the emergence of early organisms. They posit that this form of oxygen, generated through interactions with ancient metallic rocks, may have contributed to the complex biochemical processes necessary for life to thrive. Others, however, remain skeptical, questioning the extent to which dark oxygen influenced the atmosphere and the evolution of life. This divergence in viewpoints highlights the complexities of reconstructing Earth's early conditions and the challenges inherent in interpreting geological and chemical data. Adding to the complexity of the discussion is the controversy surrounding the ocean floor neural network theory, which posits that the interactions between dark oxygen and the geological features of the ocean floor could create a network of life-sustaining conditions. Proponents of this theory suggest that the electrical currents generated by ancient metallic rocks in conjunction with dark oxygen could form a neural-like network that supports diverse ecosystems. Critics, however, argue that this theory lacks sufficient empirical evidence and caution against overextending the implications of dark oxygen without robust data. This debate underscores the importance of rigorous scientific inquiry and the need for further research to validate or refute such theories. Encouraging viewers to think critically about scientific findings and debates is essential in this context. The discussions surrounding dark oxygen exemplify the dynamic nature of scientific exploration. where new discoveries can challenge established paradigms and provoke differing interpretations. It is crucial for the public to engage with these debates, understanding that science is not a static body of knowledge, but rather a continually evolving process. By fostering a critical mindset, viewers can appreciate the complexities of scientific discourse and the importance of evidence-based reasoning. As scientists continue to investigate the implications of dark oxygen, they are not only exploring its role in Earth's history, but also considering its potential relevance for understanding life beyond our planet. The ongoing discussions reflect a broader quest for knowledge, where differing opinions and controversies serve as catalysts for deeper inquiry. By engaging with these debates, viewers can gain insight into the scientific process, recognizing that uncertainty and disagreement are inherent to the pursuit of understanding our world. Ultimately, the exploration of dark oxygen and its implications invites us to reflect on the mysteries of life, both on Earth and in the cosmos, encouraging a spirit of curiosity and critical thinking in the face of scientific discovery. In this video, we explored the fascinating concept of dark oxygen and its significant implications for understanding life on Earth and potentially beyond. We began by discussing how dark oxygen, a newly discovered form of oxygen, generated through unique geological processes, may have played a crucial role in shaping the early atmosphere of our planet. This discovery not only enhances our comprehension of Earth's biological history, but also opens new avenues for exploring the conditions that could support life on other celestial bodies. The potential for dark oxygen to exist in environments previously deemed inhospitable, such as the icy moons of Europa and Enceladus, invites us to rethink our definitions of habitability and the diverse forms life might take. We also delved into the ecological impact of deep-sea mining, particularly concerning polymetallic nodules, which are rich in metals and play a vital role in supporting marine ecosystems. The discussions highlighted the need for a balanced approach to resource extraction, emphasizing the importance of preserving these ancient formations for future research and understanding of our oceans. Furthermore, we examined the ongoing debates among scientists regarding the significance of dark oxygen, showcasing the dynamic nature of scientific inquiry and the importance of critical thinking in engaging with new discoveries. As we wrap up this exploration of dark oxygen, we encourage you to reflect on its implications for both our planet and the search for extraterrestrial life. Understanding dark oxygen not only enriches our knowledge of Earth's history, but also inspires curiosity about the possibilities that lie beyond our world. If you found this video informative and engaging, please consider subscribing to our channel, liking the video, and sharing it with friends and family who might also be interested in these captivating topics. Your support helps us continue to create content that delves into the mysteries of science and the universe. We invite you to explore related topics, such as the search for life on other planets, the ecological impacts of resource extraction, and the latest advancements in astrobiology. Engaging with our community through comments and discussions can enhance your understanding and spark new ideas. We value your insights and encourage you to share your thoughts on dark oxygen and its implications. Together, we can foster a vibrant dialogue that deepens our appreciation for the complexities of life on Earth and the potential for life beyond. Thank you for joining us on this journey, and we look forward to exploring more intriguing subjects with you in future videos.